Hi all, this is Mr. Lim here, and today we're going to be talking about equilibrium vocabulary, making sure we know all of the words that we need to use when dealing with equilibrium stuff. All right, so let's have a look at what we're going to be learning. We're going to be learning how to define the following words: shifts, favors, net reactions, yield, and LCP, or Le Chatelier's principle, which is a terrible thing, but we'll go through it anyway. All right. So equilibrium vocabulary. First one is dealing with is shifts and favors. So shifts and favors are words that we use to describe which reaction is currently or will in the future be greater than the other. Okay, so it's effectively saying which reaction, that's the forward or the reverse reaction, it has a faster rate. If the reverse reaction will be greater than the forward reaction, the reaction is said to shift to the left or favor the left. Okay, so this is why we actually use this shifts and favors, because we're using a direction, left being towards the left, towards the reactants, because more reactants will be formed. Okay, it is not a replacement for the concept of net reaction, right? Which we will go through in a moment, but the idea is that we are shifting towards the left or favoring the left, or favoring the reverse reaction when the reaction is larger than the other. So what examples are there of this? Okay, so here we have in the rate of reaction graph over here, okay, at the beginning of the time period, the forward reaction is greater than the reverse reaction at the same point in time, okay? So therefore, this favors the forward reaction, and the forward reaction happens to be the right reaction, or towards the right. Okay, let's have a look at the second example. We've got a concentration time graph, okay, which is something different. We have to look at what's happening. At the beginning, we've got equilibrium. We can tell because we've got flat lines there. Then, at this point in time over here, something's happened to shift it out of equilibrium, all right? However, what can we see? We are having more reactants, less products. Okay, that makes sense. More reactants, less products, because we can see that the red line went up, the blue lines went down, and those blue lines are the products. Okay, if there are more reactants and less products, that means that the reverse reaction is going faster than forward. Okay, and if the reverse reaction is faster than the forward, that means the reverse reaction is favored. And, or we can say it shifts to the left. Okay, so we can have a look at these graphs, and the idea is that the word shift and favors just means which reaction is currently larger than the other, or going faster than the other. All right, let's move on. The net reaction. So the net reaction is the overall reaction. When taking into account the forward and the reverse rates of reaction. Okay, so if the reverse reaction is greater than the forward reaction, there is a net or overall reverse reaction. Okay, so it's the overall amount. If you're going 100 one way and 50 the other way, well then you're going to have the larger one is the overall direction of that reaction. It's important to state which rate of reaction is occurring faster than the other, not just saying that it shifts to the left, okay? Because it shows a better understanding than shift to the left and right, because some people learned to say, oh, it shifts to the left, it shifts to the right, without actually understanding which rate of reaction is going faster or what's happened to those rate of reactions. Okay, so let's have a look at an example. Here we have a rate of reaction graph, okay? And what you'll notice is that first of all, it's at equilibrium because the forward and reverse rates of reaction are going at the same time, okay? But you can see here something happens to decrease both rates of reactions. So here, both rates of reactions decrease, okay? We'll get through what causes that later on, but the idea is that both decreased. Which one is greater than the other one after that point in time? It's the reverse is greater than forward at that same point in time. Okay, so therefore there is a net reverse reaction. Now you'll notice that the reverse rate of reaction decreased, but there is still a net reverse reaction because the reverse rate of reaction is faster than the forward rate of reaction, even though the reverse rate of reaction decreased. So the reverse rate of reaction decreased, but still faster than the forward rate of reaction. Okay, so the idea is that this net reaction doesn't say whether it increases or decreases, it just says which one is going faster than the other. All right? And it's really important to remember that because which way it goes and which one is favored are two very, very different things, and which one is the overall net reaction, very different things. You need to be able to state all of them and not just one or two of them. Okay? Right. Equilibrium vocabulary. So we're doing, now we're going with yield. Okay, so what is yield? Is the overall amount of the chemical species, and it's different to concentration because concentration is dependent on the volume. So if you change the volume, you might change the yield, but also the concentration as well, and they might go in different directions. So here's a concentration time graph. What's happened at this point in time here is that the container got smaller. If the container gets smaller, that means there's less space for the reactant and product particles. So here we started off at 50 liters. You had 50 mole and 25 mole, and so therefore you have these concentrations. When the container got smaller, turned to 10 liters, at that point in time here, these two concentrations jumped up, right? Their concentrations immediately increased. However, their total amounts did not increase or decrease, that they stayed at 50 and 25. All right, their total amounts didn't change. However, over time, when this concentration changes over here, the total amount changes. All right, the reactants went from 50 to 40, and the products went from 25 to 30. So the yield of the reactants, went up or down? Went down. Okay, went from 50 to 40 moles. However, the concentration of reactants went up. Okay, and this is why it's important to understand the two different words, yield and concentration. They're linked sometimes, but they are not always the same. Okay, so the yield is the total amount, the concentration is the amount by volume. All right, in terms of the products, the yield went up as well as the concentration. So that's useful because they both went up, but not always. Okay, so you really, really have to read the question, what is it asking you for, and then answer it appropriately. Okay, and then lastly, Le Chatelier's principle. So Le Chatelier's principle, which I hate using, so you should not use as well, is a tool to help predict what the system is going to do when a change is made onto it. The principle is that the system will work to oppose the imposed change. Okay, so let's have a look at some examples. If the temperature is increased, the system will try to decrease the temperature by favoring the endothermic reaction, which decreases the temperature. If the volume increased, then the pressure will decrease and the system will try to increase the pressure. How? By favoring the reaction that produces more particles. Okay, so this Le Chatelier's principle is the part in red. Okay, so the idea that when you have a change, the system will do the opposite, and then knowing what it does is over here is the overall end effect. Okay, now ideally you don't use Le Chatelier's principle to go from the change to the end effect. You want to use collision theory and explaining stuff, and that's what we're going to be doing over the next couple of videos, right? But this is just the lazy way of doing it, which is why you shouldn't do it, all right? So it doesn't help you explain why changes can occur, so it's very poor, but this is, you just need to be able to see it so that when you see it in the exam, you're not like, what's this? All right, and so that's it for equilibrium vocabulary. Then we're going to get into changes to equilibrium systems. That's it.